So the present topic of discussion is thermal stress in bar elements. Thermal stress in bar elements. And you know, in bar elements there is uniaxial stress field. Now think of a bar which is fixed at one end and which is free to expand at the other end. Suppose the length is L. The coefficient of thermal expansion is alpha and you increase the temperature by delta T. Then it expands by L alpha delta T. But there is no stress developed because this is free expansion. So no stress developed in free expansion. Now if you hold the bar, between two rigid walls, so this is a rigid wall, this is also a rigid wall, and you increase the temperature by delta T, then there will be a stress developed in this. In this case, the expansion is L alpha delta T and the strain is the increase in length by total length. So strain is alpha delta T. So in this case strain is 0 but there is a stress developed, and the stress developed is alpha delta T E. This is the stress developed, E into alpha delta T. So here strain is alpha delta T but stress is 0, and here strain is 0 and stress is E alpha delta T. This is already known to you. So now if you draw the stress strain curve, so the stress strain curve will be something like this. The slope will be the elastic modulus, the slope is E, the slope is E, and this is actually alpha delta T. Now you see, when strain is alpha delta T, stress is 0. So when strain is alpha delta T, stress is 0. So the first condition is satisfied, and when strain is 0 means here the stress is this and the stress is compressive, and the stress is compressive. Yes, there will be compressive stress. So the stress is compressive, a minus sign for compressive stress. So this is the stress strain relation for a bar where there is thermal stress. So now we have to find out the potential energy, and you know potential energy is strain energy minus potential of loads. So what is the strain energy value here? the strain energy is, you all remember, the strain energy is integration over volume, and this is strain energy density, integration of volume. And what is strain energy density? ACD is strain energy density, and the strain energy density is integral sigma d epsilon from 0 to epsilon. So if you go up to this, so take this element, suppose this is the value of epsilon, then this is actually d epsilon, so d epsilon, so, and this is sigma, so sigma d epsilon is the area, so here this is epsilon, and you actually integrate from 0 to epsilon. So here epsilon is the integration variable and epsilon is the limit. You can take it as epsilon final or something like this. Anyway, so we are taking it the final value as epsilon and variable of integration also as epsilon. So epsilon d epsilon, this is the epsilon, and the area under this is sigma d epsilon, and from 0 to epsilon the area under the curve is actually the strain energy density. So here you see, then the strain energy density will be zero to epsilon. Here sigma is E into epsilon minus alpha delta t, d epsilon, because here the equation of the curve, the equation of this curve is sigma equal to E into epsilon minus alpha delta t. The equation of curve is sigma equal to E into epsilon minus alpha delta t. When epsilon is alpha delta t, sigma is 0, and when epsilon is 0, then sigma is minus E alpha delta t. So this is the strain energy density. So, and you must have noticed that this is the area under this curve. So this is this area minus this area. So this area minus this area, and if you do the integration, then this is E by 2 epsilon minus alpha delta t square, and this from the limit is from epsilon to 0. So this is E by 2 epsilon minus alpha delta t square minus E by 2 alpha delta t square. So if you expand, then the first term is E by 2 epsilon square minus E epsilon alpha delta t, then plus E by 2 alpha delta t square minus this. So this two term gets cancelled, and you get this as strain energy density. So what is the strain energy now? The strain energy is E epsilon square by 2 minus E epsilon alpha delta t, this integrated over the volume. Here volume is A Tx, so x is equal to 0 to L. So see, so when you do not consider thermal stress, there the stress strain law, or which is known to you as Hooke's law, this passes through the origin. The slope is again E. Slope is E, and only this term stays, this term is not there. So this is the extra term, what we get for thermal stress. Now what is potential energy? Potential energy is strain energy minus potential of loads. And now we have got the expression for strain energy. So now we look at the bar element. So this is the bar element, and here you know, so U1 F1, U2 F2, and here alpha delta T. So alpha is the coefficient of thermal expansion and delta T is increasing temperature. So here potential energy is strain energy, and strain energy is first term E by 2 epsilon square A by 2 epsilon square dx 0 to L. Let us check. So A E by 2 epsilon square dx minus A E alpha delta t minus A E alpha delta t 0 to L epsilon dx minus U1 U2 transpose F1 F2. So this is the potential energy expression. I think the second term is also correct. A E alpha delta t epsilon. Yeah. So now we know epsilon is equal to B into U1 U2, where this B is actually a row matrix for a bar element containing minus 1 by L 1 by L. So this is dn1 dx, this is dn2 dx. Now if you put it here, then pi becomes U1 U2 transpose B transpose. I am keeping this AE inside the integral, though it is constant and can be kept outside the integral, but we are keeping it inside the integral. So B, here the integral ends U1 U2, because one BU is coming for one epsilon and the other BU is coming for the other epsilon. So So this is for the first one, then minus here again U1 U2 transpose A E alpha delta T, here B transpose. For epsilon we are writing U transpose B transpose dx 0 to L. So U transpose means one row, U transpose means one row, two column, and B transpose means two rows. Here two columns, then B transpose means two rows, one column. So it is a single term. So minus U1 U2 transpose F1 F2. So this is the potential energy expression. So now you see the stiffness matrix is 0 to L B transpose. Okay, let me once remind you what we do actually is we del pi del U1 equal to 0 and del pi del U2 equal to 0. So this once this get differentiated and next this gets differentiated, and since this is a symmetric matrix, so when you add them up, they are the same term and this half goes. So this becomes K into U1 U2 is equal to A E alpha delta T B transpose. B transpose means, let us write what is B transpose. B transpose is minus 1 by L dx 0 to L plus F1 F2, where A is actually the element stiffness matrix, so you put E. KE is, as you know, B transpose AE B dx 0 to L, and this term is minus 1 by L dx 0 to L is minus 1 and this is plus 1. So the final equation is KE, the same KE for bar element which we got previously, equal to AE alpha delta T, here minus 1 plus 1 and plus F1 F2. So this is the element formulation. This is the element formulation, and this is actually the force coming due to thermostress. So now we can work out a simple example. Here suppose between two rigid walls a bar is held, and actually the diameters are different or the cross sections are different. So here the cross section is A1 E1 and the expansion coefficient of thermal expansion is alpha 1, and for this it is A2 E2 and alpha 2, and the length is L1. So now this we can take as element 1 and this we can take as element 2, and we can, for element 1 we can write down the finite element matrices. For element 1 it is A by A1, E1 by L1, 1 minus 1 minus 1, 1, U1 U2 equal to A E alpha delta T. So alpha delta T is strain, E, when you multiply it with E it becomes stress, and when you multiply it with area it becomes force. So minus 1 1 plus F1 F2. So here it would be A1 E1 alpha 1. So whole bar is given the same temperature increment, which is delta T. So for element 2 it is A2 E2 by L2, 1 minus 1 minus 1 1. Here it would be, okay, let us write it like this. So this is one element and this is the other element. So here it is fixed, here it is fixed. So this is element 1, element 2. So let us call it capital U1, this is capital U2, and this is capital U3. So there are 3 degrees of freedom. So the small u1 and small u2 actually correspond to small elements. Small u's are for element local displacements, and the corresponding system displacements are capital U1, capital U2. So here again, if you write in terms of small, it will be U1 and U2. So U1 of element 2 and U2 of element 2. Here small u1 means U1 of element 1, which is capital U1. Here U2 of element 1, which is capital U2. So here this is U1 of element 2 and U2 of element 2. So you can simply write it as, okay, so let us write it like this because that will be better. So this is U1 for element 1 and U2 for element 1, and this is U1 for element 2 and U2 for element 2. So equal to A2 E2 alpha 2 delta T minus 1 1. This is F1 for element 1, F2 for element 1. So this is F1 for element 2 and F2 for element 2. Now if you assemble, then you get a 3 by 3 matrix. If you assemble, then you get a 3 by 3 matrix. So here A1 E1 by L1, here minus A1 E1 by L1, here minus A1 E1 by L1. Here A1 E1 by L1 plus A2 E2 by L2. Here minus A2 E2 by L2. Here minus A2 E2 by L2. Here A2 E2 by L2. Here this is capital U1, capital U2, capital U3. Here this is minus A1 E1 alpha 1 so let us take delta t common, alpha 1 here A1 E1 alpha 1, so this and this, so minus A2 E2 alpha 2 A2 E2 alpha 2, and this is the reaction force on here, the reaction force from 1 and 1 dF1 and the reaction force from dF3, and here it is 0. Now since U1 is 0 and U3 is 0 because the bar is held between two rigid ends, so the first row goes, the first column goes, the third row goes, and the third column goes. So we are left with only this, 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 obviously with delta t, and this. So the final equations are A1 E1 by L1 plus A2 E2 by L2 into U2 equal to delta t A1 E1 alpha 1 minus A2 E2 alpha 2. Here I want to remind you again that finite element always works with numerical values, but in this example for better explanation we are keeping the symbolic variables. Otherwise finite element always works with numerical values, and here we will compare it with your standard SOM strength of material calculations. That's why we have kept the symbols, and we hoped that the symbolic representation will explain the process better. So now here, from here you get U2 equal to delta t U2 equal to delta t A1 E1 alpha 1 minus A2 E2 alpha 2 by A1 E1 by L1 plus A2 E2 by L2. Now once you get U2, then for the first element, small u1 small u2, so you know epsilon is equal to b, which is minus 1 by L1 1 by L1 into u1 u2, and obviously this is u1 for element 1 and this is element 1, so this is epsilon element 1, or you can write it epsilon for element 1, so this is for element 1, So this is minus 1 by L1, 1 by L1. U1 is capital U1, which is 0, and U2 is this value. So epsilon 1 becomes U2 by L1. And sigma, if you want to find out sigma 1, then what we have to do is we have to E not into epsilon 1 alone, but epsilon 1 minus alpha 1 delta t. So you have to do this to find out your value of sigma. So you remember that here you have to add this term. This is not, sigma is not E into epsilon alone. Here you have to add this part also, because this is the material relation or the constitutive relation for thermostress. So with this, for element 2 also you can follow the same procedure, and that is sigma 2 is equal to E into epsilon 2 minus alpha 2 delta t, and for epsilon 2 you have to do the same process. So let us stop here. Thank you.